Okay, so we'll start the video off with that. When we last left our physics heroes, we were talking about the second kind of waves, compression waves. So what's the other wave called? This is longitudinal. Sine wave, transverse wave, of which a sine wave is an example. So a transverse wave. And in a transverse wave, remember we looked at the little string simulator, the individual particles are moving perpendicular to the way the disturbance is moving. In a longitudinal wave, they're moving with the disturbance. So instead of crests and troughs, I have to be very slow when I say that or I screw it up, we have what in the longitudinal wave? Don't look. See if you can answer it without looking.
Compressions.
Compressions and, okay, somebody else?
Density.
Rarefactions, yes. So crests and troughs in a transverse wave, compressions and rarefactions in a longitudinal wave. Okay, so now that we've kind of just covered the anatomy of the waves, the two wave types, we're going to talk a little bit about some calculations. You knew this was coming. Okay. This is more math that you're going to absolutely love. We can measure things about waves. They all have a wavelength, they all have a frequency, and the product of that is the speed that the wave is traveling at. So the velocity of the wave. In the same medium, wave speed doesn't change. That's critical. As long as you don't change mediums, wave speed doesn't change. When you change mediums, wave speed changes. This is how we get the bending of light. Light waves, which are a form of electromagnetic radiation, when they change media, like through a prism, through water. You've all tried to grab something in the water and it's not quite where you think it is, because the light waves are actually bent when they enter the water and they move at a different velocity. So their wavelength is, well, we'll talk more about that when we get to light. Okay, so it's a three-part equation. V equals F lambda. I want you all to practice writing a lambda because you'll look really, really smart when you can write lambda. So it looks like an upside down Y. Some fonts give it the little widgets on the top, but you don't have to do that. Lambda is wavelength. So lambda is the letter of the Greek alphabet that's used to signify wavelength. Okay, so you're going to like these because they are like the simplest possible three-part algebra. If you'd be so kind as to look at 457. Okay, so this is from page 457 in your book. These are the 12D problems, and you're, like I said, you're going to really like this. So here we're talking about a string in the piano. So this is a sound wave. This is, well, it's a wave on a string, which would then create a sound wave in the air. The speed as this string vibrates, the vibration is transferred into the air and travels at 343 meters per second, which is a pretty standard value for speed of sound in air. We won't get to do the whole sound chapter, but we'll get to do some of it. The frequency of the vibration is 264 hertz, and what the musically inclined among you will find fascinating is that all a note is, it's a given frequency. And you may already know that, but like concert A that orchestra's tuned to is 440 cycles per second, 440 vibrations per second rings the note in your head that we agree is called A. So this is a middle C vibrating at 264 cycles per second, so 264 vibrations per second. What we want to know is the wavelength of the sound waves produced by this string. So we're solving for lambda. V divided by F equals lambda. Of course, you would always want to show your rearrangement because that's how we roll. So we have 343 meters per second divided by 264 hertz. What's a hertz? A hertz is 1 cycle per second. Yeah. So often given as 1 over seconds. You'll see why that's important when we do a little bit of dimensional analysis here. So 343 divided by 264. Okay, so you should have a raw number, something like this, 1.2992424 on and on and on. What are my units? Meters. Why do you say that?
Because they're 1 cycle per second.
Ah, okay. So if you do some dimensional analysis, meters per second over hertz, which is 1 over seconds. When you invert that and multiply, guess what you're left with? Meters. So I just want you to remember that hertz is 1 cycle per second. If you solve something algebraically and you end up with 1 over seconds, you've solved for hertz. If you end up with seconds, you have not solved for frequency, you've solved for period. So you have to be careful with that. Okay, we have 3 sig figs, so 1.30 meters is lambda. So what that means, just to bring this home conceptually, if somebody walks over to middle C and goes doing and plays a middle C, 1.3 meters away is the sort of the end of the first wavelength. So it's actually that distance in space to get an entire cycle of motion. Same for a wind instrument or an air-driven instrument like a bagpipe or a clarinet or anything else. That vibration with that note, 264 cycles per second, it's going to be a whole 1.3 meters away to complete a cycle of motion in air. I just find that kind of fascinating. So assigned, of course, are all of those. So 457, which is the 12D problems, 1 through 4. But I think you'll find them pretty straightforward. Okay, so we're not going to stop to work on those today. Let's move back to business, folks. We know that waves are a disturbance in a medium, yes? They transfer energy. They don't transfer matter, they transfer energy. So let's see if we can do the wave again. Is it worth trying again?
After lunch.
You guys were so bad at it.
After lunch. I need to have a full tummy to do this.
No, let's try it right now. Okay, go.
I don't have energy.
So, waves are a disturbance in the medium. They don't transfer matter. You guys did a wave. You didn't leave your seat. You didn't even stand up. You certainly didn't end up someplace else. The only thing that moved was your body's in place. So this disturbance traveled through the medium. The particles didn't move. That disturbance is really a form of energy. So waves transfer energy because if we get right down to it at the most tiny little nitpicky level, particles are moving. That means they have what? Kinetic energy. So that kinetic energy is being transferred through the medium. Now, the rate of energy transfer is all about amplitude. Remember which part of the wave sort of anatomy is amplitude. Let's do that. The what? Okay, so yeah, the amplitude is essentially the height of the wave. It's the distance away from equilibrium. It's how far away from equilibrium the wave gets. The amplitude is really what you look at to know how much energy is being transferred. So that's the key to the energy transfer. What's interesting is it's proportional to the amplitude squared, which means if you double the amplitude, you have 4 times the energy being transferred because it's amplitude squared. I can guarantee you that is a concept I will ask you about. If you cut the amplitude in half, you divide it by 4. If you triple the amplitude, how much more energy are you transferring? 9 times. So quadruple the amplitude, you're transferring 16 times as much energy. So it is proportional to the square of the amplitude. It's not a linear relationship, it's an exponential relationship. Okay, does that make sense? Okay, so now we're going to talk about interference. And you've already seen a little bit of interference when you guys were, when we had people standing up here sending waves back and forth. And you said, well, they keep coming back. Yeah, they do. And they would interfere with one another. So interference is what happens when you have 2 or more waves that interact. They come together in some way. You see this, now ocean waves we have to be careful with because they're what's called a surface wave because they actually exist at the boundary of 2 media, and so it's not straightforward, but we can use them as a rough example. You see interference with ocean waves all the time, or Lake Erie. If you've ever stood on the shore and watched waves come in, even up at Pymatuning, a smaller lake, as one wave is coming in, another wave is going out, and you see changes in the incoming wave as a result of the motion of the outgoing wave. That's interference at its simplest. What happens is you actually have the two waves superimposed. And we can do this with both mechanical waves, so transverse and compression waves like sound. You can also do it with electromagnetic waves. If you have ever heard blurry, muddy sound as a result of echoes, have you heard this? So one of the examples that the marching band people will be immediately familiar with. When I was in high school, we used to march at the old Latonia Field, which was up on the hill in Latonia, and they had this great little like metal backstop. And when the band was up close playing near that metal backstop, from the perspective of being in the band, we sounded god-awful. Why? I mean, we sounded terrible. And we were pretty good that year. Why did we sound so bad? Our sound was actually hitting that wall. It was coming back. It was interfering with the sound waves we were producing, and it was actually changing them. And so we were like off key and out of tempo, and it was just terrible. We sounded fine in an open field without that metal backstop. We would have been just fine, but we were experiencing interference. So that's interference in a mechanical wave, because a sound wave is a mechanical wave. It's a wave in air. It's a compression wave too, which we won't get to since we're not doing the sound chapter, but that's an example of interference. Electromagnetic waves, light can interfere. So we're going to do a quick demo. This is actually an app that I'm going to pull up. If I can find a way to screenshot it, I will, and then we'll put it in the notes. We've got our picture here of constructive and destructive interference. And wherever, like I said, wherever we see these yellow bulges, these, okay, so all the yellow there, that is all constructive interference. Wherever we see the dark spaces, which is all of this, yeah, the skinny purple lines, that's where we have the destructive interference. So we have this pattern of alternating areas of constructive and destructive interference. Okay, what that looks like. One of the cool things about doing this is we can actually graph this on the Doceri. So if we take this as our equilibrium position, and it's nice because we can use two different colors here, and we have one wave that looks like that. And we take another wave that looks like, we'll see if this contrast works, like that.
Yeah.
Okay. Let me actually fix this a little bit. Okay. Those two waves are going to have almost entirely constructive interference. Okay. So at every point, and let's move this down a little bit. At every point along this line, if we actually plot points here, so in essence, we're taking little vertical snapshots. The resultant wave, and I'll do that one in black, is going to be the sum of the two waves. So if this is, let's see, 1, 2, 3, 4, 5, 6, 7. So 4 plus 7. This is actually going to be up here. And we could go through every point and plot the wave. And I've had students do that in the past. I don't know how effective it is. I think there's one of the homework problems I'll assign that will have you do something similar. Now here, they're both 0. That's going to remain 0. Here we've got 2 and 2. That's 4. Here we have 3 and 5. That's 8. So we start to build a picture of this much bigger wave, and you can kind of see it's going to look something like that. That's a real fast and dirty, sort of rough approximation. Yes. Now, what happens if the waves that we have look like this? Well, you're still adding them, but one's negative. One is the inverse of the other. So, you know, and if I had drawn this as perfectly as I had it in my brain, this would completely cancel. And it's not drawn that perfectly. It doesn't really cancel. But what you get is, you know, you get a cumulative wave. That's constructive and destructive interference. So this is constructive. This is destructive. Now, what's usually the case is that it's not a perfect picture of either. And what we sometimes like to look at is cases where we have these sort of weird, oh, wait. We'll just do it for one wavelength to keep life easy. So things that are sort of out of phase with one another. Well, there are points where that's going to have constructive interference and points where it's going to have destructive interference, if I've drawn it well. Yeah. So if we kept this line going, you know, in this, in this area, we're going to end up with some really funky, weird patterns. And you end up with waves that do things like this. I mean, they get really strange if you really start doing constructive and destructive interference, especially when the wave, we would call these waves out of phase, meaning the crest of one is occurring just behind the crest of the other. They are slightly out of phase. If they were perfectly in phase, their crests would line up, their troughs would line up. You'd have, you know, maybe different amplitudes, but same top and bottom. You'd have the same top and bottom points. So what we'll do is we'll stop the notes here. When you come back, we're going to look at what happens if you have a pattern of repeated constructive and destructive interference. Okay?